All right, let's dive right into the heart of Bitcoin. We're going to look under the hood at its engine. So, how can this global digital currency work with nobody in charge? I mean, no CEO, no central bank. It sounds kind of impossible, right? But the answer is this really elegant piece of engineering. Let's get into it.
So this is the big puzzle. If literally anyone can join the network and participate, how do you stop it from just turning into total chaos? How do you make sure that everybody agrees on who owns what without some kind of central referee to make the final call? This is the core problem that Bitcoin was designed to solve.
To really get the solution, let's first imagine a super simple system run by just one person. Let's call her Lisa. She's in charge. She processes all the payments. But, well, this gives her absolute power. So if Lisa decides she doesn't like John buying cookies, she can just deny the transaction. Poof, no cookies for John. And what we just described, that's a central authority. It's a single point of failure and a single point of control. This kind of censorship is exactly what Bitcoin was built to prevent. The whole idea is that a financial system shouldn't depend on the whims of just one person or one entity. Okay, so a simple fix might be to just add more people, right? Let's bring in Tom and Chi to help Lisa. The problem is, now they're all creating blocks of transactions at the same time, leading to all these different conflicting versions of the payment history. It's complete chaos. This is a problem we call block collisions. So what if we tried something else? What if we held a lottery? To avoid all that chaos, we could say only the person who draws a lucky number gets to publish the next block. And if, by chance, two people get lucky at the same time, we just follow a simple rule. The longest chain of blocks becomes the official one. That settles any ties. But here's the fatal flaw in that system. It's completely based on trust. How do you actually know Tom or Chi really drew a lucky number? They could just lie. They could just publish a block and say, hey, look at me, I got lucky. There's no way to prove they're cheating. The whole system just falls apart. And this brings us right back to our core problem. We need a system that forces people to be honest, but without having a boss watching over them. We need a lottery where you can't just claim you have the winning ticket. You have to be able to prove it. And that proof has to be totally undeniable. And this is where we get to Bitcoin's brilliant solution, proof of work. Instead of a lottery based on trust, which you can see on the left, proof of work is a lottery based on pure computational effort, which you see on the right. Honesty isn't just a suggestion. It's forced by cold, hard math and the real-world cost of electricity. So we no longer follow the longest chain. We follow the strongest chain, the one with the most work poured into it. So what is this work exactly? Well, you can think of it like a massive digital puzzle based on something called a cryptographic hash. A hash is basically a unique digital fingerprint for any piece of data. It's a one-way street. Super easy to create the fingerprint from the data, but basically impossible to work backward and figure out the data just from the fingerprint. So miners, like our friend Chi, are just constantly trying out different numbers, called a nonce, that's short for number used once, and adding it to their block. They just keep guessing until they stumble upon a nonce that makes the block's hash start with a whole bunch of zeros. Let's watch Chi go to work. She grabs a bunch of transactions, makes a block, sets the nonce to 0, and calculates the hash. The result? It starts with AA9C. Nope, that's not what she's looking for. That's a fail. So she's got to try again. And again, and again, and again. Let's fast forward a bit. Here she is on her, 227 millionth try. The hash starts with a whole lot of zeros. She is getting so close, but it's still not the winner. The only thing she can do is just keep guessing. And finally, after over 492 million attempts, she finds a nonce that spits out a winning hash. And this right here, this is the magic of proof of work. It was incredibly difficult and expensive for her to find this number, but for anyone else on the network to check that her number works, it's instant, it's effortless. That is the proof. But this system creates a new kind of problem. What happens when more and more people, attracted by these rewards, join the mining race? Well, with all that extra computing power, the winning numbers get found much, much faster. The system is supposed to produce a block about every 10 minutes. But as you can see here, with more miners on board, we're finding them way faster than the goal. The whole system is speeding up. So how does the system deal with this? It adjusts itself automatically. Every 2016 blocks, the whole network basically pauses. looks back, and checks how long it took to find them. If it was too fast, the puzzle gets harder. If it was too slow, it gets a little easier. This difficulty adjustment is what keeps the block time ticking along at that steady, predictable 10-minute pace. Okay, so now for the ultimate test. Can a bad actor, like Lisa, use this system to cheat? Let's say she pays a cafe for a cookie, but then she secretly starts trying to create an alternate version of the blockchain where she pays that same money back to herself. This is what's known as a double spend attack. Now, for this to work, Lisa has to privately build her own fraudulent chain of blocks that is stronger, meaning it has more proof of work than the honest chain that literally everyone else is working on. It's a race, but she's just one miner, and she's competing against the combined power of the entire rest of the network. As you can see, she is falling behind, fast. The math here is just absolutely brutal for an attacker. I mean, look at this table. Even if they somehow controlled a massive 36% of the network's computing power, their chance of success just plummets with every single block the honest chain adds. Once they're 6 blocks behind, their chance of catching up is a tiny 3%. It's basically game over. And that number, 6, that's exactly why you'll often hear people in the crypto world talking about waiting for 6 confirmations. For any high-value transaction, a merchant is going to wait until that payment is buried under 6 new blocks. At that point, the transaction is considered irreversible, locked in place by just a massive wall of computational work. Okay, but why would anybody spend millions of dollars on computers and electricity just to do all this work? What is in it for them? The answer is the block reward. It's the prize you get for winning that computational lottery and finding the next block. This reward actually has 2 parts. The first and biggest part is the block subsidy. This is a set amount of brand new Bitcoin, just created out of thin air. It's how new coins enter the system. The second, smaller part is the sum of all the transaction fees from the payments that were included in that winning block. So what does this all mean? What's the big takeaway? Proof of work isn't just some technical trick. It's a brilliant economic solution. It cleverly takes the simple self-interest of miners, their desire to earn a reward, and channels it into a powerful force that secures the entire network. By competing for that prize, they collectively make the network honest and trustworthy for everyone else. And that kind of leaves us with a final big thought. This idea of using verifiable, costly work to get a group of people to agree on something without needing a central leader, that's an incredibly powerful concept. It's the engine that powers Bitcoin, sure, but where else could it be applied? What other systems, far beyond just money, could be rebuilt on this foundation of decentralized trust?